Good afternoon. My name is Fadi Kamal. I wish you a blissful holy month. First of all, let me start by a very short disclaimer for this webinar. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, and exclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real perceived conflicts of interest. The information contained within this presentation by ASHRAE Pyramids Chapter as a supplier stakeholder webinar, it presents information of current interest to avoid a venue for interaction between ASHRAE Pyramids members, the different industry stakeholders, and the webinar presenter. These webinars should not be considered peer-reviewed or final word on any subject. ASHRAE Pyramids Chapter has not investigated, and ASHRAE Pyramids Chapter expressly disclaims any duty to investigate any product, service, procedure, design, or the like, which may be described herein. The appearance of any technical data or editorial material in this presentation does not constitute endorsement, warranty, or guarantee by ASHRAE Pyramids Chapter of any product, service, process, procedure, design, or the like. And first of all, our topic today is how to order CFD reports for healthcare facilities and isolation rooms. Let me start by introducing our honorable lecturer, Professor Dr. Ahmed Medhat. Professor Dr. Ahmed Medhat is a full-time professor of mechanical engineering since 2012 and official consultant at Architect and Housing Institute, HI, at Housing and Building National Research Center, HBRC. Head of MAP Technical Reviewers Committee at HBRC, Professor Dr. Ahmed has graduated from the Faculty of Engineering at Cairo University at 1988 and got his master's and PhD from the same university at 1993 and 1999 respectively. He started his career at 1985 in Coldair, which was the oldest HVAC equipment manufacturer and MAP contractor related to the governmental sector. After graduation, he continued working in Coldair till 1998. After getting his master's, he worked for many international consulting firms for design and supervision of different HVAC and fire engineering projects. During 2002, HBRC elected him to join the researchers team as a mechanical researcher and consultant to participate in preparing and updating HVAC and fire codes with participating in ventilation, HVAC, Arab and energy efficiency, and the Green Pyramid Rating System, GPRS, for sustainable designs and evaluation. During the last 20 years, he has published more than 60 scientific, academic, and practical papers in international journals, conferences, which are devoted to HVAC, energy efficiency, and indoor environmental quality. Professor Ahmed has established his private consulting firm during 1992 named Luki Egypt. Luki is working for both of perspective and performance-based design supervisions for different HVAC and fire engineering projects. Luki has more than 25 years experience in Middle East working for continuous education, engineered HVAC designs, CFD predictions validated by field tests of smoke management applications and fire strategies, also HVAC climate control systems. At 2015, Professor Ahmed became a certified HVAC and smoke management consultant. He develops and conducts a series of seminars for HBRC, TUV, GTZ, ASHRAE, Cairo and Pyramids Chapter, and Egyptian Fire Protection Association. Lastly, Professor Ahmed conducted more than 30 technical articles in HVAC versus fire engineering for HBRC. He is currently sitting on HBRC committees for HVAC, energy efficiency, life safety, and smoke control committees. This is the bio of Professor Dr. Ahmed. Also, I would like to remind you all that we have a section for questions. If you have any questions, please leave them in the questions section in the GoToMeeting, and we will try to answer as much as possible. And I'd like to give the stage or the mic to Professor Dr. Ahmed. Please, Professor, start.
Okay. Thank you, Freddy, for this nice presentation. And I want to check, is the screen of the presentation is available now?
Yes, we can see it.
Okay. Good afternoon, our respectable colleagues. Today we will discuss how to order a CFD report. If I want to prepare special designs that are not listed in the local codes, and we need to use the performance-based designs, and we will discuss what is the difference. Okay, performance-based designs, it's a way of the codes that can use the modeling, numerical modeling, and the simulation programs to validate or to assure that this design will satisfy what was designed for it. At the beginning, the basic codes, most all over the world, the codes that are commonly used are the prescriptive codes, which declared very clearly the minimum requirements by fixed parameters. For example, don't exceed the amount of air than 500, for example. Don't exceed the velocity. This is what we call it the thresholds. And there's another type of codes, trade-off codes, okay? And this is something in between the prescriptive code and the performance-based code used normally for the building envelope designs. You can state a value for a performance of the building envelope, okay? And then you can make any design you want just to reach to the value stated for the performance for this envelope. Third one, the performance-based code, and this is what we call it the whole building approach. This is now became a commonly used, especially for in fire engineering. It is used when we try to utilize the jet fans for ventilation and so on. But in our case, when we are talking about the healthcare facilities, we need the performance-based option or performance-based code to state developed systems and to assure that these developed systems will work in a proper manner, same like the prescriptive code. And our case study is needs for robust indoor environmental quality within HCF, it means the healthcare facilities. Indoor environmental quality, to summarize it, is a combination between the indoor air quality and the thermal comfort and the visual comfort and the acoustics. In our task, because we are talking about the air conditioning, we will talk about the indoor air quality, okay, and the thermal comfort and other issues. The remaining acoustics or visual comforts could be discussed by other disciplines. So, if we need to improve the indoor environmental quality to assure that there is no cross-infection or even infection from outside to any place in the healthcare facilities, so we have many. We introduced many designs for the air distribution, for the relative pressurization among different zones, a lot of things. Now we are meet the coronavirus. Okay, previous researchers on SARS before shows some issues that could be commonly between SARS and coronavirus. For examples, one of the gained data is during the cough, okay, there is a droplets coming from the patients, okay, about 3,000 droplets. And during sneeze, it could be reached 40,000 droplets. And by the way, the droplet, we consider it 5 microns, okay? But for up to my knowledge, that COVID-19, the size is it's not fixed all the time. It ranged between 80 nano to 200 nanometers. So this means that each droplet will contain a lot of viruses inside it if it's 5 microns. We have another thing. We need some way to scavenge any viruses stayed on the surfaces or the copper, in the bed, on the furniture, on plastics, on chairs, on sofas. Okay, so how we can scavenge this? So at the beginning we have to know, okay, how many hours can stay this virus in the ambient condition? How many hours shall it stay? For example, we have here this figure shows for copper the virus. This is the half-time age of the virus. What we mean by half-time age, the decay time. It's equivalent to the decay time. So if you have, for example, some viruses here, for example, 5,000, now here will be 2,000, will be here, but still exist. So for the copper surfaces, the viruses can stay 4 hours. For cardboard, can reach 16 hours. Okay. For stainless steel, can reach to 21 hours. For plastics, could be reached from 20 to 21. This is very important to know that beside the cleaning, the continuous cleaning and sterilizing of all the goods around us in the healthcare facilities, we need something can scavenge or drying all these stayed viruses. Another point here, the effect of temperature and humidity and sunlight of the SARS virus decay. This is not for COVID-19, but this is one of the corona series. We can say here that during the normal conditions from 70 to 75 degrees Fahrenheit, this means about 20 to 24 degrees Celsius, and with a relative humidity 20%, okay, and without the effect of daylighting or solar, okay, so the decay in minutes will be 1100. It's been about 16 hours or 15 hours, something like that, less than this. And the temperature, if it's stayed as it is, but the humidity increases, so the decay time will be reduced. If you increase the temperature and the humidity, okay, you will reach 1 minute decay time. If you continue, or go back, sorry, to the normal air conditioning temperature, 70 to 75, with 80% relative humidity, okay, and with the presence of the sunlight, okay, you will have maximum 2 minutes and the virus will dead. Okay, the same. We cannot say that this is an exact table for our situation, but it's a guide for us to say that beside the social protections, social distance, cleaning hands, everything, sterilizing all the goods around us, we can control very well the viruses in the air or in the surfaces by our systems. Word of wisdom says one of the professional expertise in the numerical and physical modeling, my professor, said that everybody believe an experiment, except the one who did it. But nobody believe simulation results except the one who did it. Now, we want to make an order. If I'm the manager of the hospital and I want to make an order for CFD to study an isolation room, we can move a little bit forward to see what we have. Our case is very simply, it's a compound for isolation rooms. It's a compound for isolation rooms. And this compound, it's about 45 meter length by 50 meter width, and the height is 4 meters. It includes a typical single and double isolating rooms. They have the same size, okay? 7 meters length by 4.5 meter width by 3.2 height. One of them, this is the single room, has an lock at the beginning. This is the door here. You can see it here, the door here, and this is just an airlock. And this is the water closet. To another door here. This is sliding door. This is swing door. Okay, so you go here. You will find a screen, a curtain around the patient bed. And you can see here we have a linear slot diffusers at the top, and this is 2 lighting fixtures. Here you can see the medical equipment. This is the door with transfer grill for the water closets. This is the exhaust grill. This is the refrigerator. This is the television set. And here a sofa and a portable bed for any guest. The 2 beds like this, and you have also the same curtains. This curtain started from 40 centimeters from the finished floor up to 2 meters, and the height of the room is 3 meters, 3.2 meters. Okay, you can see here, this is the patient, and this is the medical equipment also. The concept here is similar or nearly similar to the laminar flow. All this compartment, it shall be installed on a raised floor. So we will have a supply air from this slot diffuser, and we will collect the air, whatever, if we use it as exhaust, or it will be returned after sterilized. Okay, whatever, but it will be sucked through the raised floor. Okay, and the supply air will be here. So we have exhaust here or return, and exhaust here or return, and here the supply air. At this airlock, we have a separate air washer from here, and return near to the floor also. What are required to show? We have to go back 20 years ago, 30 years ago, before CFD became a popular solution for the performance-based design or performance-based option. We used before the analytical solutions. Okay, we can use similarity principles. We can use the dimensionless group to make the modeling or the simulation. Okay, but it's not a simulation and it's not modeling, it's a pure solution. So we have to see the flow of air inside the room, and we have to see the drop, the spread of air coming, the asymmetry of the temperature, and the same also for the relative humidity. We have to have a fixed temperature in the vertical direction to avoid any stratification. Could affect on the patient or affect on the doctors and the people inside this room or watching the patient. Adding to this, the local air velocity is very important. The induced and we call here the room air that penetrate inside the air coming from the jet, which delivered from the supply outlet. Okay, this is what we call it the induction ratio. All this together, we call them in two equations: the draft temperature theta and the air diffusion performance index. This means that we will use this factor, okay, to validate or to guide us, okay, if our CFD or simulation going in the correct way or not. I don't need to go in detail of the air diffusion performance. I described the situation of the air distribution inside the room. It is not a factor for the outlet. It is of air outlet type. If it's a square, ceiling, register, grill, slot, swirl, whatever, and also it's a function of the characteristic length of the room. Not any length, the characteristic length of the room and the relation between the location of the outlet and the direction of these characteristic lengths. Third, it's a function also in the air distribution layout of air inlets and outlets, the number of outlets, the location of them, the height of them. Okay, all these are very affecting parameters that could be very declared clearly in the air diffusion performance index. The room thermal load also, and here we can consider a very important issue that the walls and the heat coming from the wall are all from the external wall as a part of the building envelope, and the glass and the partition, the floor and the ceiling, all these parameters as a heating load watt per square meter or BTU per hour per square foot will be considered inside the air diffusion performance index. Finally, the throw and drop distance. This means that it's a very important throw and drop. Normally, they are important in the temperature difference between the supply air coming from the outlet and the average room air, plus the jet velocity coming from the outlet. Here we can see simply, this is the equation of the effective draft temperature, and here the air diffusion performance index. The details of these equations, you can find it in all references in ASHRAE handbook, fundamental in details, and how you can use it in reality. Again, we need to another important issue, what we call it local mean age of air in a zone, LMA. If we are talking in a hospital or in an isolating room, we bring air from outside and we sterilize it, clean it very carefully, and treat it, cooling or heating, whatever. and heat it inside the room. If the room is isolating, very critical, we have to use fresh, 100% fresh air, same like intensive care or operating rooms, okay, to avoid any recirculation of these infections. Sometimes we made it positive pressure and negative pressure. For example, if the patient has a problem that could be affected by any other disease, like AIDS, okay, so his room shall be 100% positive pressure. Okay, in our cases, in isolating room could be for corona COVID-19 could be positive pressure, but sometimes we can make it relatively negative pressure. Actually, the zone compounds will be positive pressure, but relatively, isolating rooms will be highly relatively positive than the corridors. It will be highly, this is a graduation of the pressure distribution. Now, the local mean age, what it's mean? It's mean how many time, how many minutes, how many seconds. This means that our case is time dependent all the time. Time dependent. The time it's a factor. If I want to scavenge viruses from the surfaces, okay, I have to consider the time. If I want to calculate the local air diffusion performance index, I have to check the time, okay, and the change of the draft temperature with the time. To calculate the local mean age of a zone, so I have to study after how many seconds, okay, this air reached to certain concentration, okay, and we can compare it with the ideal case, the case of piston effect of air, where you feed the air from side and bring it from the other side. This is what we call the optimum. Why? In this case, we called it the ventilation effectiveness. But back to local mean age of air, this is very important factor. And as we mentioned here in this slide, it is defined as the average time in seconds that air has spent in a zone of the building accumulating contaminants, whatever these contaminants, viruses, dust, fungus, whatever, bacteria, whatever. And it is an important factor in assessing the quality of ventilation. Now we have the last point in the empirical correlation that we can use it to assure of the our designs, the ventilation effectiveness indices. And these are two groups. Group A, the air exchange efficiency indices can be used for cases where little or no information on contaminant sources is available. This is first group. The second group, okay, where we defined the CRE, the contaminant removal effectiveness, the efficiency of the system that you design, okay, to remove all contaminants, and we measure it to the base of the optimum case. Here the definitions. And this some ideas about the air diffusion performance index. By the way, for the common places like offices, commercial buildings, air diffusion performance index shall not be less than 80%. This means that we need to be more than 85 to 90% for the isolating rooms. And here you can see the room loads, okay, as a figure, and the throw at 0.25 meter per second of the characteristic length. Okay, this you will find that the maximum ADPI 68, whatever, some here, some points 94, whatever. Now, for the modeling procedures, as we mentioned that we have this compound, okay? So this compound shall be, first of all, we need to use the CFD in our case. And we mentioned that our case designed 40 or 50 years ago with numerical correlations. Now we want to make some changes in the air distribution inside this isolating rooms. This will be typical rooms. We have this, this is the single bed. So first of all, if you want to order, okay, you have to ask that the gate geometry shall be considered. If you want to make some simplification to simplify the system, it's okay, it could be done, but the simplification that has a minor effect on the system distribution. Here you can see the details. You can see the curtain, and this curtain here designed as a strips, 15 centimeter wide strip. Oh, sorry. And the length of it is about 2 meters. Okay, it could be transferred.
Professor Ahmed,
it's not important.
Professor,
Now?
this is Freddy. Sorry for interruption. Can you try to turn off the webcam so that the sound quality be better, because sometimes some interruptions happen to the connection.
The webcams, close the webcam.
Your webcam.
Okay.
Yes.
It's okay.
Thank you. Please continue. Yes.
Now, you have to know the windows with its material, and our diffusers has 2 slots, each slot about 5 centimeters. We have a TV, it's a source of heat, refrigerator, it's also a source of heat. The location of the or exhaust grills, okay, at the floor level, and the bed, and here the water closets or the toilet. Okay. After drawing, complete drawing, we have to make the meshing, and this is the.
Professor, sorry for interruption again. The presentation slide is the same. It's not changing.
No, it's changed. Moment.
Okay.
It's okay. Now.
Yes. Yes. That's good.
It's okay.
Yes, it's working. Yes,
Check.
please.
It's okay.
Yes.
Okay. Okay. Now for the modeling procedure, we have to make the meshing. The meshing, at the beginning, to think about the meshing, you have to think, what do you want to see in this room? If you want to see the air coming from the outlet, this means that to allow the CFD to see the outlet, this tool shall have some points inside this outlet, inside the 3 centimeters or 5 centimeters separated in the outlet. This means that you have to prepare a very fine grid. Okay, but the very fine grid, this means that you need a lot of grids inside this room. And a lot of grids, computers, it's been a lot of time. Anyway, in our case here, we use a mesh size to check the valid one for this case 5 millimeters by 5 millimeters by 5 millimeters, including 1 million cell. Here we need to see very fine for that, because we need coming with the aerosol, and you will see this in the videos. All these items needs a very fine, and we have the second one. In the market, we have a lot of abilities and a lot of type of unstructured grids. It could be used here. You have to ask for the experience, and the experience is the accumulation of trials. So your trial for simple cases or even complex cases, okay, it will add a knowledge to your experience to judge on this case what the best type of mesh shall I use, and what is the aspect ratio of each mesh. The aspect ratio, which means it's a relation between the hydraulic diameter to the height of the mesh, if we consider it as a cone. So to generate the solving domain, the mesh in the solving domain, we have to select type of grid, the aspect ratio of it, shape of it, the size of each grid compared, okay, to the detailing level in that domain that you want to study, and the total number for proper meshing. But we have to remember the time required for solving. In our case, we have to define the turbulence model. The turbulence model, it's a model that enables us to solve the turbulent intensities inside the flow. And in our case, we will use two types of turbulence model, the direct numerical simulation and the large area simulation, and we try to compare with them. In our case, they have the same solution, nearly have the same solution. And here is the difference between this turbulence model and that within 10% in the results, in the gained results. Okay, so it could be accepted. Model, whatever. You can see these are velocity models. You can see the difference in the colors. For sure, we need a very high resolution screen and make it bigger to see the details here. But by sense here, you can see the distribution on the horizontal cap plane here, and here you can see the difference in velocities. These at a certain time. I think here 3 minutes. After 3 minutes, and this is after 3 minutes. Also, you can see the distribution also of the air velocity here compared with this. Okay. This for the single bedroom, and this is for the double. But here also, the sizing of mesh completely different. Here was 5 millimeter by 5 millimeter by 5 millimeter, but here it's zoning. I mean by zoning that we take the first 1 meter on the horizontal plane in the room in a mesh model, and the second 1 meter in another mesh size, and the third one at the outlet location, okay, with another size. There were 1 centimeter near the outlet and 5 centimeters at the patient, okay, this one, and at the ground it was 5 centimeters. Here still 5 millimeters. You can see also the effect of the mesh size for the temperature, the same. You can see also here for the 2 bedrooms. This means that it is not enough for us to construct a geometry in very good shape and include all the details. And also, it is not enough, okay, to put the details of your system and the appliances inside the room and the expected doors. In this case, by the way, but it's not presented here, we have a cyclic opening of the door. A cyclic of what happened, what will happen, okay? Here you can see also the relative humidity, the change in the relative humidity, the same time, the same place, but here, these 2 screens, okay, with the bigger cores, what we call it, cores cells, more than 5 centimeters by 5 centimeters by 5 centimeters. You can see here, we will introduce now the results of, for example, for the video. This means that you have to solve, okay, based on the time. And we will find this very clearly when we go to the tracer gases. Okay, we can stop it and we go to the next. Oh, this is the velocities. This is vector. You can see the vectors in the 2 planes also. For sure, presentation does not explain all the clear data, but you can predict here what is the size of meshing that we used. Most of the softwares that are available in the market, what we call it CFD softwares, can produce an Excel sheet, okay, for all the points you may define. For example, if you have 3 million grid cells and you want to see the results every 3 seconds for example 3,000 points around the patient bed, okay, you can bring it in Excel sheet, and after you take it in the Excel sheet, you can go it and calculate it. Okay, calculate it for the draft temperature and air diffusion performance index, and calculate all the numerical. Compare this with your results. Here the relative humidity, the same. By the way, these case studies that we are describing now, we have 40 case for the air distributions and for the number of air exchange, because we need to make the design able to scavenge or dry any residuals of the sneeze or cough, okay, to scavenge it or dry it, okay, so it can be moved with the air to the floor and go out, and then in the void of the rest floor we can sterilize it or whatever. Here's the contamination, and please, here, this is the effect of sneeze. These small particles, okay, represent the particles, the 5 micron particles, okay, and you will find it decreases. And then you will find that the patient will sneeze again. I hope that the video can show it clearly to you. Yes, you see it. The most important issue in this design is that we take all the air to the floor, all the contaminated air to the floor. Okay. So our summary now, we can conclude what we introduced today very quickly, that CFD, it's not a design tool, it's a tool to predict that our design is workable and satisfy the previously mentioned thresholds in any code. This is the first point. In our case, our thresholds in the isolating rooms will be the thermal comfort conditions, the air change, the number of air change, the cleanness, I mean, the noise, the temperature, the relative humidity, all this together. But at the same time, all this together shall be controlled to avoid any generation of the viruses or fungus. So we are talking about thermal conditions and indoor air quality. And these will be a function of the time all the day, because all the day the patient could be sneeze or cough, and all the day the doctors could be inspect this 2 or 3 times per day, plus the other services, foods and medical materials. So you have doors shall be open and closed. This means that we have to control the pressure also. So we have to control the temperature, the local velocity, the pressure, the humidity, okay, and the air contamination inside this room. So our order will be as it is. Please, we need to see, okay, a certain time or certain interval after removing the cooling load, because we don't need to consume a time because our simulation will be function of time all the time. Okay, so we can see after, for example, 2000 minutes. Okay, after 1 day, 2 days, for example, I'm sorry, one day, 2 days. This will need a lot of time to simulate it, and this is what we are doing now. But we reach 20 hours, okay, for each room, whatever filled by slow diffuser or bar outlet or swirl diffuser or standard diffusers. And we have two cases. One of them the exhaust and the return is at the floor, and the other will be at the only the four corners of the room. So again, we can say in the order we have to declare that you have to put in your model full scale model, okay, and the simulation or the modeling will be time dependent. Third, okay, the geometry shall be installed completely in details, okay, and you can make some simplicity of the geometry, but you have to keep the main parameters of the similarity principles as it is, like Reynolds number, parameter number, Archimedes number, Stanton numbers, all these dimension groups. You have to define clearly the scope of study within the volume. Okay, if you want to study the air coming from the outlet or the air around the patient or the air around the doctor, okay, you have to consider this because this will have a great effect on the sizing of the meshing. You have also to mention in this report, show all concentration references, means that all concentration are taken as values above the value in the supply air, because you will bring the fresh air with a certain amount of CO2, CO2 or a certain amount of helium, whatever, or a certain amount of non-toxic gases that will not have a bad impact on the patient, and then you compare it with the final before exhaust. Then select the grid and consider the 5 parameters that we said before. Prepare at least grid here by the grid independent, like what we did. Try to test. Here you can say, I want to make some simplification to make it faster. To test your grid, okay? If I use the grid, okay, with tetrahedral or hexagon grid, and they give me the same or nearly the same results, so it's good. So you can continue. And also take care of the aspect ratio of the grid. Okay, the aspect ratio has a limit according to the characteristic length of the enclosure that you study. Okay, then you can size can increase, make it coarse, make it fine grids, and up to 20% deviation. Okay, so no problem, you can proceed. Okay, but in our cases, we don't allow more than 10% deviation in the grid independent sites. After that, you have to declare in this report that all the boundary conditions shall be considered typical as the reality. Okay? We cannot say in any case study like this, okay, we can consider this wall adiabatic. This is constant pressure. No, we have to follow the reality, because if you give the computer a bad data, he will get a very bad result. Then we have to, after we put the boundary condition, we have to select the turbulence model. What type of turbulence model? And we believe all the time that we have to check 2 types of turbulence models to be sure and to have our self-satisfaction that this both turbulence models give us the same or nearly the same results. By the way, item 8 and 9 and 10 are will consume a lot of time. Output result from the CFD shall show temperature, local velocity, relative humidity, contamination concentration, turbulence intensity. Then whatever, you take it as an Excel sheet and you will process it outside, or you can use it inside the software. Okay, you can give a programming module to the software to make side calculations to calculate the thermal comfort, the predicted mean volt, PMV. This is you can find the TC and PMV and PPD percentage of people dissatisfied in the ASHRAE 55. ASHRAE 55, yes, for thermal comfort. Then you can calculate the local mean H. Okay, this could be estimated. Okay, and then air diffusion performance index. You can input the equation of the air diffusion performance index inside the simulation program. Okay, to calculate it for you. Also, here this is it's repeated again. Air change effectivenesses. Okay, this is gives you after how many hours. Okay, the room will be clean. Okay, and here the contaminated effectiveness and the air quality index. All this could be calculated as we mentioned before. And finally, we have validation our case study. And we can, after we finalize one case, we can compare it with the prescriptive codes. What said before the prescriptive codes? Okay, and for my age, 30 or 35 years ago, okay, how they solve it? We have to use a lot of literature reviews, especially that literature reviews that use the experimental investigation for the full scale or even physical reduced scale and full scale modeling to compare this by this. You can use also similar researches. Okay, you can do it with your suggested meshing or turbulence model, and you can compare the result. All this will increase your experience, and also to make an order for the CFD modeling. You can put it in one page and introduce it to the company that will make this to follow, okay, and to give you what you want exactly. Thank you for your attention.
Thank you a lot, Professor Ahmed, for the presentation and also for being on time, because we have actually a handful of questions. So first of all, many of our attendees are asking about the material and of the presentation. So are we able to share it with them?
Sure. Yes.
Okay. If you have no problems with sharing, I'd like to tell all our audience that I will upload the slides of the lecture. I will upload it and I will post the link on our Facebook page, ASHRAE Pyramids, and on the Facebook page. So please expect to find it on maybe today or tomorrow maximum, so that you can download it. Second of all,
I will send it to you after 1 hour.
Okay, no problem. After you send it to me, I will post it on our Facebook page, and anyone who is interested to download the slides, please just check our Facebook page and download it from the link.
But excuse me, Freddy. Excuse me, Fadi.
Yes.
They may face a small problem with the videos. The videos, I made it very quickly, but the video is about 400 megabyte. So I don't know how.
No problem.
All right, perfect.
It's no problem. Yes.
All right.
Okay, so we have some questions here. So we have a question from Kanaya Patel. He's asking, ceiling supply and floor return is recommended for an isolation room. Is it recommended?
Till now in Egypt, okay, no problem to use it, but it's very costly. But what is it's commonly used here in Egypt, according to our hospital code, okay, you can feed the air from the top and suck it from the sides, not from the floor. You can suck it from the sides, or even as the standard what we use, you can feed it from the ceiling and take the return from the four corners on the ceiling also. So there is no stringent regulation for the supply and return air, okay, for the isolating. The most important issue in our local code is whatever you have to define this room will be positive pressure or negative pressure. This is the first point. Number two, no infiltration or exfiltration from this room at all. Number three, to satisfy the ASHRAE recommended thermal comforts. Okay. That's all.
Okay, thank you, Doctor. Also, we have a question that was asked by many of our attendees also. What is the CFD software that you suggest and the CFD software that you are using, Professor?
There is a lot of softwares in the market, okay, but after a while, after 5-10 years, you will find that this software, for example, Fluent, it's perfect. If you want to make a simulation for an opera, Fluent will be very nice, okay, but it needs a very robust and heavy computer workstations. I can say mainframes. If you want to make a whole like the opera with 2,000 persons, okay, and to simulate person by person, okay, Fluent, it's perfect. Also, EDA-ICE can do what EDA-ICE, it's Finnish software or Swedish software. It's a little bit complicated compared with Fluent, okay, but can do the same as Fluent. You have also phonics. You have also Jasmine, whatever. For example, in this case, two cases in our model here, we use PyroSim, which is called FDS. FDS is software prepared for the fire dynamic simulation. Okay, what is the problem? If can solve the continuity, momentum, energy, radiation, diffusion, okay, equations, and can deal with the 3 or 4 turbulence models that are popular, okay, and can accept the boundary conditions. So what is the problem? Okay, the problem is that if you want to make a validation of your results with others, what is the popular in the market now? Okay, you will find in the Middle East Fluent and FDS and SES. SES, this is software also for subway environmental simulation. This is for subways, but can solve. Okay, Transys also. Okay, it's available in the Middle East. In North Europe, you will not find all this. You will find EDA-ICE, you will find Transys, okay, you will find the basic codes. So it depends on what is suitable for you, okay, and what is suitable to solve your problem, because you can bring the best software in the world and you switch off, okay, the diffusion equation, switch off from the menu, from the internal menu, so the program will not calculate it So be sure that, and most of these programs now they are able to solve most of the cases, but there is a specific. And by the way, also our cases is simple cases. We are not solving an atomic reactor, or we are solving what happened in the internal combustion engine during the spark. No, we are dealing with a simple. You can consider it a simple case.
Okay.
So, next.
Yes. We have a question from Nasim Tamari. He has actually 3 questions. What is the turbulent model that has been used in the simulation?
We used here 3 types, K epsilon, K omega, and K omega failed, but K epsilon it's worked good, and large eddy simulation. We use the 3 to compare and check. Yes.
The second question is controllability of temperature. Is it based on MRT or operative temperature or air dry bulb temperature?
What happened in the reality? What is the actual things that happen in the rooms? Dry bulb temperature, because the sensor is thermistor or semiconductor inside the thermostat, okay, and it's covered, so it's totally shaded. So what is facing? It's facing only the dry bulb temperature, so the control will be dry bulb temperature. You got the point, or it's not clear?
Yes. We have another question from Dr. Ayman ASHRAE. Can we fumigate a disinfectant solution with the air supplied to the system to control the contamination?
Again, I cannot understand this question.
I think he means, can we inject a disinfectant solution to the air supplied to the system to control the contamination?
Look, I couldn't understand the question also, but I can suggest what he is looking for. Look, all the time we are trying to feed very good quality of fresh air, 100% hygienic, right? Because we are talking about a healthcare facilities. Then this air coming inside the room and to remove the thermal load and to remove the odors, smells, all the things, and then we took it again. If it's returned back to the machine, it's okay. If it's threw it away as an exhaust, it's okay. But if you want to take it from an isolation room, so you have to sterilize it, to re-sterilize it. Okay, at least if you want to use it again. This is the concept here of this investigation, is that we will use for the compound, all the compound, we will use a full outside air handling unit that feed all fresh air, treated fresh air, sterilized with plasma or with ultraviolet, okay, and feeding the room. And we will suck the air from the room in the rest of the floor. And with the use of the ultraviolet lamps, we can kill any viruses or any bacteria, anything could be killed. At the same time, it is not allowed to expose the ultraviolet to the humans, whatever. Okay, so we want to make it inside the rest of the floor, totally isolated. Okay, and bring it back. Okay, if the air quality and the number, the concentration of the carbon dioxide and VOCs, the volatile organic compounds inside it, it's a little bit high, so we can mix another air with it. But if not, we can exhaust it. This is very costly, by the way, because the air and the unit full outside air, okay, will consume a lot of energy to cooling the air for tropic regions from 40 degrees Celsius till 15 degrees Celsius. This is the concept here that we are willing to use the series type plate heat exchangers to make a recovery of the exhausted air. We need to make a recovery to be economic. We have to make a recovery of 70% of the cooling load of the cooling load in the exhausted air, okay, to make a pre-cooling of the fresh air. At this time, it could be efficient system, little bit consuming energy, but 100% hygienic. Okay, I hope that I answered on the question.
Yes. I think we can take one or two more questions. So we have a question from Amritansu V. Do we use K epsilon for the simulations as we look at the bulk properties?
Can we what?
Do we use K epsilon for the simulations as we look at the bulk properties?
What do you mean by bulk properties?
I'm not really sure.
I cannot understand what is the bulk properties. Well, anyway, Carson proved that he can validate in many cases. Okay, not validate. It's workable for many cases and situations. Okay, but in some cases that have an aerosols effects, okay, Carson will not work efficiently or could be the correct turbulence model when you have a great mass transfer with two-phase flow. Okay, K-Epsilon, I tried it 2 times before. Okay, maybe we can face it in our cases because we are still working on this research, because we need to make this compound to be prefab. If you want to install it, okay, in a week, you can do it. It's very easy to construct and 100% durable and dependable systems.
Okay. One last question from Mustafa Abdelalim. Which tutorial one should follow to go through Fluent software? So do you have any tutorials do you recommend, Doctor, or what is the best way to learn the software?
For Fluent, this question is related to Fluent.
It's for Fluent, but I guess Fluent it can be more generalized.
Yes. No. Fluent, it's a company called ANSYS. ANSYS has a special modules for the air conditioning, by the way. Okay, but you have to pay for it first, and it's not commonly available for the educational version of the ANSYS. So in a way, you have to purchase it. Tutorial, you can use the standard tutorial that available on the website of ANSYS, or he can visit our chapter. Okay, we have the old versions of the tutorials for ANSYS, for Fluent, because at this time, the old times, it was Fluent. We can give you a copy of the chapters that he wants, okay? Because these old versions are printed in a detailed manner and with all the description. So you can contact Pyramid chapter, and we have the electronic library. We can give you what you want.
All right.
Yes.
We have many questions, but I think because now due to the restrictions of time, And we want this topic and presentation to be as light as possible and also as straightforward as possible. If you have any more questions, please send it to us on our Facebook page, ASHRAE Pyramids Chapter. Also, I found some people asking that they don't have Facebook accounts and they'd like to download the material. So I will write now the website of our of ASHRAE Pyramids, and you can find us on Facebook on ASHRAE Pyramids. I'm writing it right now on the chat. So please check the chat. If you'd like to download the materials, just search for ASHRAE Pyramids on Facebook, or check our website, but maybe I will post it later, or maybe at the end of the week or within the end of next week, I will post it on the website. So be posted. At the end, I'd like to thank you all for attending this webinar, and I believe this will be the first of a series of webinars. As you know, Professor Ahmed is the president of ASHRAE Pyramids, and we made also a series of videos with engineer Ahmed Abdelghani to address the coronavirus issue in the HVAC field. So also please check our YouTube channel on ASHRAE Pyramids to find these lectures. Unfortunately, it's in Arabic, but we are trying now to translate it and post the translated one as soon as possible. At the end, I'd like to thank you all for attending. These are very unconventional and unusual circumstances, and we hope that we be more closer together, and so that we can overcome this issue. Also, this is an initiative from us, ASHRAE Pyramids chapter, for attendees from other chapters. If you are from an organizing committee, if you are involved in your chapters and you would like to make a cooperation with us, we can host a webinar together to address different topics and to address different point of views, and because it differs from country to country and from a region to region. So if you would like also to cooperate with us, please contact us on the Facebook page or through the website, and we will be more happy to cooperate. At the end, Professor Ahmed, I'd like to leave the closing of this webinar to you. If you have any final message that you would like to say to our attendees, please say it.
Yes, thank you to all of you, and for you, Fadi. And also, I want to thank my colleagues in Lucky office, Engineer Muhammad Ramadan, and Engineer Yasser Ali, and Engineer Samir, who are working in this research. And I believe that within the next few weeks, we can introduce the complete solution in another webinar, but it will be in Arabic to make it simple. Thank you very much again, and
thank you, Dr. Ahmed. Thank you. Have a good day, all.
Thank you. Bye. Bye.